Dr. Shobana Narasimhan, today's speaker, to the audience. Shobana Narasimhan did her BSc from St. Xavier's College, Bombay, and her MSc from IIT Bombay, where she was the Institute Silver Medalist. She obtained a PhD in theoretical physics from Harvard University. She did postdoctoral work at Brookhaven National Laboratory, USA, and the Friedhaber Institute, Berlin, Germany. Since 1996, she has been on the faculty of the Theoretical Sciences Unit at Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. She is a fellow of the Indian Academy of Sciences, the National Academy of Sciences, India, and the American Physical Society. She is also an international honorary member of the American Academy of Arts and Sciences. In addition to her research in computational nanoscience, she has a strong interest in issues related to gender and science. And today's topic is my journey as a materials girl. So, madam, for your information, so physically, here almost 30 of our girl students, and are one by there are 100 and that's starting from and after completion of 25 lectures, we are compiling it into an annual commemorative volume. So we have already completed 3 volumes, and this is the fourth series of actually SOAFAL lecture on Lilavati's women scientists of India, and already 6 women scientists have already delivered their talk. And today is the 7th one. So I am very privileged, madam, and on behalf of the university, of all the students, we welcome you, and I hope this will be a very interesting session. And today, and then at the end of the lecture, for 10 to 15 minutes, we'll have questions and answers also. So, with these words, once again, I request Madam Professor Dr. Narasimhan to deliver the SOFAL 4 series operation. Thank you, Madam.
Thank you so much. I'll just share my screen and I'll. Can you see my screen now?
Yes, madam. Yes.
One sec. Let me make it full screen. Okay. So, thank you, sir, very much for your kind introduction and also for this invitation. It is a great privilege to be invited to give this talk. I'm going to talk about my journey as a materials girl. So I was asked to start by talking for a little bit about myself and my journey. So I thought I would start, especially since this is a series featuring women scientists. I thought I'd start by telling you a little bit about my maternal lineage. So because I think it's interesting way of seeing how life has changed for Indian women over the generations, and also how, despite the various constraints that they have operated under, Indian women have always been very strong, very driven, and have achieved a lot despite the various disadvantages they had. So this over here is my great grandmother Lakshmi. She was married when she was just 8 years old, and she didn't really want to get married. She was playing outside with her friends, and her mother-in-law to be told her, if you come and sit down inside here, I will give you a mango. So she liked mangoes very much, so she came and sat, and then she got married. In those days, it wasn't very common for the girl to be sent at such a young age to the husband's house. But in her case, her mother-in-law very much wanted to raise a girl child. She only had sons. And so she took Lakshmi already at this age of 8 to her husband's house. And Lakshmi then was educated by her mother-in-law. And she also became a very well-known singer In those days, it was not considered very common or very respectable for women to sing or to learn from men or to sing in front of men, but she used to do all those things. Then this over here is my grandmother Sugandha, who was also a very talented singer. She learned to sing and play the veena from her mother Lakshmi, and she got married when she was 18 after she finished school. But she went on to have four children, one of whom was my mother. But after getting married and having children, she studied by correspondence and she did her BA and her MA. And she also opened a music school. This is my mother, Shakuntala, who was doing her PhD in economics when she got married. But she was married at the age of about 22. But when she got married after about a year, I was born. So she wasn't able to finish her PhD at that time, which was something she was always rather upset by. So when many years later I got my PhD, I told her, Amma, see, now I've got my PhD. Now it's your turn. You go and finish your PhD. And she went on to actually get two PhDs at that age, one in women's studies and one in music. She became a very well known writer and musician. She's a singer, but she was also a award-winning journalist. And this is, of course, me. And I did not get married. I have a PhD, and I'll tell you more about my life. So that's about my mother's side. About my father's side, my father grew up in a small village called Tandre in Tamil Nadu. This here is a picture of my father's family. This little boy here is my father. He grew up in a very traditional Brahmin family in Tamil Nadu. But from a very young age, he was fascinated by mathematics, and he always decided that he wanted to be a mathematician, even though he wasn't very clear exactly what a mathematician was. And he went on to become a very famous, internationally famous mathematician. So this is a picture of my father and me when I was young. My father passed away about 3 years ago. And here I just put two of the tweets that were tweeted after my father's passing away. One is by Ed Witten, who is possibly the best known physicist alive today. And the other is by our Prime Minister, Narendra Modi. So, with these two people as parents, it's perhaps not that surprising that I grew up to become a scientist with a strong interest in writing and in women's issues. So, I grew up in what was then called Bombay. So, I went to school, college, and IIT there. Then, for my PhD, I went to Harvard University in the US. Then, after my PhD, I did a first postdoc in Brookhaven National Laboratory, which is in New York State in the US. Then I sort of came halfway back home. I went to Germany to the Fritz Haber Institute in Berlin. And then in 1996, I came to the Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore, which is where I still am. So this is a picture of my class in school. So this girl here with the two long plaits and the somewhat sad face is me. So I went to the Convent of Jesus and Mary. It's a Catholic school. It's an all-girls school. I think it was a very good school. And amongst other things, I was never made to feel at this school that there's anything that I cannot do because of being a girl. I was never told, oh, girls can't do this or girls can't do that. I felt I could do anything I chose to do. Now, it was at school that I first encountered physics in the eighth standard. The way the physics was taught by the teachers I had there was not particularly inspiring. It involved a lot of rote memorization. For example, I particularly remember for some reason how we were taught Boyle's law. Each girl in the class had to recite what Boyle's law is. The pressure of a given mass of an ideal gas is inversely proportional to its volume at a constant temperature. Then the next girl says it, then the next girl says it. If anyone says it wrong, you were made to go and stand outside the class. Okay, and what was the result of this? I certainly hated physics. At that age, I would never have imagined that I would become a physicist. So in Maharashtra at that time, the 11th and 12th standard were done in junior college. So I joined St. Xavier's College in Bombay for my 11th and 12th standard. This was the first time I was in a co-ed class, but it was a very unbalanced class in terms of gender ratio. It was a class of 75 students, of whom only 4 were girls. And especially after I sort of topped the class in the first midterms, a lot of my first encounter with what I call the loneliness of the female scientist. But in 11th standard, that was the year, that was the birth centenary of Einstein's, it was Einstein's birth centenary. And I was asked if I would do a radio program about Einstein and his work. And prepare for this program, I started reading a lot of physics books about relativity, about quantum mechanics, etc. And I got so fascinated by what I read that I decided then, in a complete change of mind, that I want to become a physicist. And after that, I was just really, really fixed, sort of completely focused on becoming a physicist. And I've already mentioned my parents to you. Here on this picture, I put some of my father's famous books and papers, and this is some of the books my mother wrote about women's issues. I wanted to say that my parents were completely supportive of my choices. They never said, oh, you shouldn't do this, you should do engineering, you should do medicine. They gave me total freedom to follow whatever interests I had. And I know that not everybody is so fortunate to have this kind of support from their parents. I also had, I think, a very unusual upbringing and unusual group of friends, because I grew up on the campus of TIFR, the Tata Institute of Fundamental Research in Bombay, because that's where my father worked. And nearly all my group of friends went on to get PhDs in physics. So here I'll just put the names of some of my friends: Ila, Sunita, Chitra, Malan, Bhavani, etc. I've said, they got their PhDs in biology, computer science, physics, maths, etc. from very good places in the US. I had only one friend, Yumna, who got her PhD in English. I'm hearing somebody else speaking. Okay. So then I went to do my BSc from St. Xavier's, and then my master's in IIT Bombay. The gender ratio was not quite that bad in these places, but in IIT, only 5% of students were female. Then I went to Harvard University as a PhD student. And in Harvard also, the classes were overwhelmingly male. Like in my batch of 30 students who admitted to do PhD, only 2 were women. And in the next year, of about 30 students, 3 were women. So this is a picture. This is me over here. And this is 2 of the women in the year below me. This is Elizabeth. This is Catherine. And remember Elizabeth because she will feature in my story later. So how is it at IIT? I found that it was not very friendly at all to women doing science. IIT, Harvard, everywhere. there were people would make, I won't go into all the stories here, but people would make all kinds of jokes about women. Like when I joined IIT, there was a debate about what should be the official symbol of IIT. And one of the men said it should be sunglasses to symbolize the blind eye they have to turn to the ugly IIT women. When I was at Harvard, the person I shared my office with, when he was bored, he would just pick me up and hold me upside down. He'd call it conversion therapy. In IIT, I had things about me painted on the road. In the US, it was quite common that people would look at me and assume that I was the secretary of the department rather than a student. So these are the kinds of things that constantly reminded me that women weren't really supposed to be studying science or physics. So since 1996, I've been a professor at JNCSR in Bangalore. Here are some pictures of our campus. This is a picture of me with some of my students. I wanted to tell you that JNC really is a fantastic institute. For example, in 2019, the journal Nature, you may know that Nature is possibly the top scientific journal. It ranked institutions worldwide normalized by their size. That is, it accounted for the fact that a small institute will produce fewer scientific publications than a larger institute. And when it did this, see, Jawaharlal Nehru Center for Advanced Scientific Research was ranked seventh in the world. And we were ranked ahead of some very famous American universities like Princeton is 10th, Stanford is 11th, MIT is 12th, etc. So I also have a strong interest in teaching physics in developing countries. I've gone to many countries across the world to teach physics, especially I have been several times to Africa. So this is a picture. Here I am in the red sweater after at a workshop where I was teaching in South Africa. This is a picture of me in the middle with two of the women I have taught and mentored. This is Anne Justine, who is from Cameroon, and this is Winnie, who is from Kenya. And both of them are now lecturers at the universities in their home countries. So, what do I enjoy besides physics? I have many interests. I like reading, I like writing. I not only like solving crosswords, I also like to set crosswords. So, if any of you read the journal Resonance, every month I set a crossword in that journal. I like painting. This, for example, is a drawing I did of my grandmother Sugandha playing the veena. I am very interested in art, so I like to visit museums. I also like cooking and baking. This is a tart that I made. I like sewing. I like traveling. So this is a picture of me with some of my students. Here you can see we are in Paris in front of the Eiffel Tower. I like spending time with friends. So before I go on to tell you about my science, I just want to tell you a little bit about what the situation is for women in science and why that disturbs me and what I'm doing about it. So historically, of course, the number of women in science and technology has been very low. For example, this is a picture, a very famous picture taken at the Solvay conference in 1927. And they're very famous scientists here. For example, this is Einstein, etc. And this is Marie Curie, and she's the only woman amongst these 27 men. But the sad thing is, okay, that was 100 years ago, but things haven't changed that much. This was a picture taken at a conference that I went to, and you will see that amongst this whole group, actually, there are only two women. One is me. I am here hiding in the corner, and there's one more woman here. So that's sort of shocking to think that 100 years later, after Marie Curie, things haven't changed that much. So this is a picture of the world where the countries are colored according to how many women scientists they have, what percentage of their scientists are women. The darker the color, the greater the percentage. And in most of the world, this percentage is less than 50%. And here are some statistics for the world. So in the whole world, 28.8% of scientists are women. But if you divide it up by the part of the world, there's some numbers that might surprise you a bit. Like, for example, in the Arab countries, it's 39.8%, which is pretty high. In Central Asia, it's 48.1. So they have almost equal numbers of men and women. Similarly, Latin America and the Caribbean. But if you look at North America and Western Europe and Sub-Saharan Africa, the numbers are almost the same, 31 and 32%. So how about India? Where do we stand? When I first saw the numbers, I was really shocked by this. Okay, India has one of the lowest in the scientific community across the world. So these are the numbers for Asia. The height of the bar tells you what percentage of the scientists in that country are women. So India has about 14%, and the only country in Asia that has a lower percentage than us is Nepal with about 7%. So that really surprised me. And it's, I think, a very sad number that we have to do something to change. So here are the percentage of women among the faculty of 97 leading institutions. So divided by subjects. So in biology, now we say there's a lot of women faculty in biology, but how much does a lot mean? It's still only about 25%. Okay, then it's math, computer science, physics 13%, earth sciences 14%, chemistry 11%, engineering 9%, etc. This data is taken from a website called biaswatchindia.com, which maintains statistics about the number of women in different fields in science in India. What about what they call positions of power? This picture was taken a few years ago. It was in 2018. It shows the President of India, the DST secretary, the directors of the IITs, the directors of the ISERs, etc. And when I saw this picture, the first thing that struck me, that really shocked me, was that in this whole group, there isn't a single woman. Okay, things are a little better now in the sense that, okay, first, the President of India is a woman. The Director General of CSR is now a woman. There are one or two DST institutes where the director is a woman. But for the IITs, right now, there is no woman director, though there's a newly established IIT in Africa, which will have a woman director. And none of the ISERs also have women directors. And why do we have so few women in science in India? So if you look at the percentage of PhDs in science in India that go to women, the percentage is pretty high. It's about 44%. But if you look at the percentage of working scientists in India who are women, that percentage is very low. So this is what I call the waterfall, that most women in India will lose to the scientific workforce after they've obtained a PhD. It's possible that other people have also talked to you about this. And I find this, I call this the enigma of India, the very surprising thing, because if you look, for example, at airplane pilots, which is also a field which is very dominated by men, if you look across the world at different airlines and what percentage of their pilots are women, the three airlines which have the highest percentage of women are Indigo, SpiceJet, and Air India. Okay, SpiceJet is no longer in existence. This was a few years ago, the statistics. But okay, the number is still not high. It's still only 14%, but it's still more than the rest of the world. So why do we have more pilots than the rest of the world, but fewer scientists than the rest of the world? I do not understand this, and I think it's something we can think about and discuss. Okay. One second. Okay, but of course we have some high-profile women scientists. For example, in ISRO, there are many women who have high positions. For example, one second, let me just see it says my battery is running low, but I have plugged it in, so let me try to understand. Okay. So this is Muttaya Vanita and Ritu Karida, who are both held very high positions in ISRO. And this picture on the left was very popular at the launch of Mangalyaan. It shows women working in ISRO congratulating each other. These are some of the top ISRO scientists. But I was a little upset. I don't know if any of you saw this movie, Mission Mangal. It was about women working for ISRO, and it shows this woman who gets her ideas for the mission when she sees puris puffing up when she's making puris. I don't know if that's a good thing or a bad thing. In some ways, it irritates me because I feel women don't only get ideas for science when they cook. We are also trained scientists. We get our ideas in the ways we've been trained to think scientifically. But also, I think perhaps there is a point in this. It tells you why you need to have a diverse scientific workforce, because if people have a diversity of experiences and backgrounds, then there are more ways in which people may get ideas and be able to contribute. And because I've been very upset about this fact that we have so few women in science and they are not always treated well, I decided to start what are called career development workshops for women in physics. These I've been holding at an institute in Italy, and women from all over the world, women here, and we share our experiences. There are training workshops. We meet successful women. We're taught to become more confident, etc. So women from about 80 countries have participated in these workshops so far. And I told you I'll talk about my friend Elizabeth again. So she's now Vice Chancellor of a university in the US, and she and I organize these workshops together. And we also held one such workshop in an institute in Rwanda for African women. And this is a picture that was taken at the conclusion of one of our workshops. This is me over here before my hair turned white. And this saying is what one of the participants said. She said, "Sometimes I think that I'm alone, but this workshop is a good antidote to that feeling." Okay, so now for the remaining time, I will tell you a little bit about my scientific work. So I work as a physicist, as a condensed matter physicist at the border of physics, chemistry, and material science. So operates the Bronze Age, the Iron Age. And for me, I'm particularly fascinated by the Bronze Age because bronze, unlike stone or copper or iron, is a man-made material. I don't like using the word man-made because it's a bit sexist, but it's something made by humans. It's an alloy of copper and tin. And to me, it's remarkable that already 5,000 years ago, 6,000 years ago, people realized that if they took two metals and mixed them, they could make a new material that had superior properties. So how many materials exist in nature? This is, of course, the periodic table. There are 98 naturally occurring elements, and composed of these, there are about 4,000 naturally occurring minerals. But we're not restricted to this. This is a periodic table made out of Lego blocks. And the whole point is that we can make new materials out of these elements. And that's what we do as material scientists. or condensed matter physicists. We understand why materials have the properties they do, and once we get this understanding, we use it to design new materials. And the materials that have already been found fill lots and lots of volumes in a library. Of course, nowadays it's all on the internet. And if you try to estimate how many such materials could be made, if you look at quaternary compounds, that is compounds made with 4 elements, it's estimated that there may be 10 raised to 11 possibilities. And if you look at quinary compounds, that is those with 5 elements, that number goes up to 10 raised to 13. Now, this is obviously a huge space to look in, and it's a very daunting prospect. You need to find some systematic way to search here. So I want all of you to stop a moment and tell me what you feel was the most important discovery of the 20th century. So those of you who are watching online, maybe in the chat box, you can write what you think important discovery of the 20th century. Like I've put some common answers here, like this is penicillin, antibiotics, this is the car, this is an early computer, this is the plane, this is television, this is the internet. So different people have different answers to this question, but one answer which a lot of scientists believe in might surprise you, which is that a lot of people believe that the Haber-Bosch process is the most important discovery of the 20th century. So what is the Haber-Bosch process and why is it important? So let me first tell you what the Haber-Bosch process is. It's a way of combining, most of you would have studied it in school or college. It's a way of combining nitrogen and hydrogen to produce ammonia. So in this picture, you see nitrogen and hydrogen molecules come and sit. So the nitrogen molecules are made of 2 pink blobs, the hydrogen molecules of 2 green blobs, and they come and sit on this catalyst. The bonds break. You will see that in a minute. This is the bonds breaking, and then they recombine to form ammonia, which then leaves. Now, the really important thing here from the material science point of view is that this happens when they sit on a catalyst. So the question is, what catalyst should it be used? So before I come to that, let me tell you why this was so important. It is because Haber and Bosch discovered what catalyst they could use that we are able to sustain such a large population on Earth. So this graph on the x-axis is time in years, and this on the y-axis is the population of the Earth in billions. Okay, so this lowest curve shows how much of the world is fed by synthetic fertilizers. So before that, let me first show you the red curve. The red curve shows how much of the world population we can feed using food that is produced without using synthetic fertilizers. But the actual world population is this blue curve. So how do we feed the rest, the gap between the red and the blue? That is this black curve. And these people are all fed using food produced by synthetic fertilizers. Now, these synthetic fertilizers are mostly ammonia-based fertilizers. And the reason we can make these ammonia-based fertilizers is because we have the Haber-Bosch process to make ammonia. In fact, this is rather shocking number, which says that half of the nitrogen in our bodies, we all have nitrogen in our bodies, half of that nitrogen came from the Haber-Bosch process. Okay, like it was made in a factory using the Haber-Bosch process, and then it was turned into a fertilizer, and then food was grown, and then we ate that food, and then it is in our bodies. Okay, so how do we, Haber had to find out what catalyst to use. Now, when this process was developed, they tried about 2,500 materials. before they decided to use iron. Now, iron was actually not the best catalyst they found. They found osmium was better, but osmium was very rare, so they decided to use iron. Now, this is a trial and error or brute force method. Now, I've told you that now we have to look amongst 10 raised to 11, 10 raised to 13 possibilities. This we really can't do by trying everything system. You can't do a brute force search amongst 10 raised to 13 possibilities. So we want to do what's called rational materials design, which requires a to and fro between theory and experiment. So I'm a computational physicist. Why do we do computations? We do it because it's cheaper. We can work from home. That's sort of a joke, but it is true. I mean, as a computational physicist, you can work from home. And especially for people who have, health issues or have family responsibilities, etc., this is a better field to go into from that point of view. Calculations on the computer are often quicker than doing the experiment. They can lead to greater understanding. Now, in a lab, we can easily create conditions that can be, on the computer, you can create conditions that can be difficult to achieve in a lab. For example, if you want to know what happens to the iron at the center of the earth, that iron is under very, very high pressure, and you can't necessarily create that higher pressure in your lab if you want to see what happens. But on a computer, you can do that relatively easily. You can switch off some effects. For example, if you want to see whether this material possesses this property because of relativity or not, in your calculation, you can say, I will do the calculation with and without relativity and see if there's a difference. And we can make predictions for experimentalists to verify. Okay, so what is the basic problem we're trying to solve? It's called the quantum many-body problem. So when we have a material, it has some number of nuclei and some number of electrons, and they interact via the Coulomb interaction. Okay, so examples are atoms, molecules, condensed matter systems. And for this system, we know how to write down an equation for this. It's called the many electron or many body Schrödinger equation. But, okay, so there's also this condition that the solutions have to satisfy the Pauli exclusion principle. But this is very difficult to solve. So let me tell you why it's difficult to solve. So you may know that in classical mechanics, it's easy to solve a two-body problem. For example, in the top picture, I've shown the Earth moving in an orbit around the sun. That's a two-body problem. We can solve it analytically. We can find an equation for the trajectory of the Earth around the sun. That's what Kepler's laws give us. We know that there's an elliptical orbit. Similarly, quantum mechanically, if you have a two-body problem like the hydrogen atom, where you have an electron going around a proton, we can solve this. We can write the Schrödinger equation for this and solve it analytically. So these two-body problems are pretty simple. However, supposing we now add one more body to the problem, we have a three-body problem. For example, you can have the Earth, the Sun, and the Moon. Or this example I took from the movie Star Wars, where Luke Skywalker lives on a planet called Tatooine, which orbits around not one sun, but two suns. Or quantum mechanically, you can have the helium atom, where you have not one electron, but two electrons going around a nucleus. These are all three-body problems, and they become very complicated. We can't write simple analytical solutions for this. We have to do it computationally. And though we can find a solution, it's much, much harder than the two-body problem. Now, if you do condensed matter physics or solid-state physics, then you have a huge number of nuclei and electrons. I mean, you have of the order of 10 raised to 23. I say 10 raised to 23 because of Avogadro's number. And they're all interacting with each other. And this is more or less impossible to solve by just solving the many-body Schrödinger equation. So this was described very nicely by the physicist Dirac. He said, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. So we can write down the equations. The difficulty is only that the exact application of these laws leads to equations much too complicated to be solved. So I do something called density functional theory, which is called DFT for short. So how does it solve the many-body problem? I won't go through the mathematical description. I will just try to tell you by an analogy. So what map the many electron problem onto an equivalent one electron problem? Okay, so supposing you have a group of men and women who have complicated interactions between them. Some like each other, some hate each other, some love each other, etc. And you are told that the problem you have is you have to arrange them all so that globally you have achieved the greatest amount of happiness. This is similar to the problem we have when we have the many-body Schrödinger equation problem. We have a bunch of nuclei. You can think of them as the blue men, and electrons. You can think of them as the red women. And you have to arrange them so that the energy of the system is lowest. This is our many-body problem, which is too complicated to solve. And what you do in density functional theory is that you map this instead to a one electron problem. So you have only one woman and you have to decide where to put her. Now, there is some green face masks I've put on the guys. I will not go into that. There's a reason I've put them. If you want, I can talk about it in the question answer session. Okay, so the amazing thing is that this solution, the solution to this complicated problem, is exactly the solution to this simple problem. Okay, so this was shown by a physicist called Walter Kohn, working with his collaborators Hohenberg and Sham. And this is such a remarkable achievement that Walter Kohn was given the Nobel Prize for this in 1998. So what you do if you're doing DFT like I do, you have calculations for which your only input is atomic numbers and atomic masses. So that is, there's no empirical input. You don't take information given to you by an experiment. You do everything from first principles. And then you crank through the machinery of DFT, which is a complicated computational task. And then you get remarkably accurate output. So because I don't have much time left, I'm just going to give you one example of research from my group. We work on a lot of different things. And if you're interested, please go look on our webpage or look up our publications or contact me. Okay, so this I'm going to talk to you about supported metal nanoparticles. So I'm going to give you one example why supported metal nanoparticles are important. So if you have a car, in the car, there's something called a catalytic converter. So the car, when you combust petrol or diesel, a lot of poisonous gases are produced, like carbon monoxide, or things that are bad for the environment, like nitrogen oxides, hydrocarbons, etc. So we don't want them to just be emitted like that into the environment. So they pass through this catalytic converter, which has small metal nanoparticles on an oxide substrate. And this is a catalyst that helps convert the bad emitted gases into less harmful products. So the example I'm going to talk to you is, can we change the shape of a material? So if you have these nanoparticles, they tend to clump up. That is, the shape of the nanoparticle tends to be a three-dimensional shape, like this pyramidal shape I have shown here. Okay, in this particular case, I've taken the example of a gold nanoparticle, which has 20 atoms and it forms this three-dimensional shape. Now, we believe that these three-dimensional shapes don't make good catalysts. And we would believe it would be a better catalyst if it can be made flat and two-dimensional. But it doesn't want to be flat. So is there some way we can coax it into being flat? So using density functional theory, we showed that if you have, for example, magnesium oxide, which is shown here as the substrate, if you do what is called doping the magnesium oxide, so you replace some of the gray magnesium atoms by these purple aluminum atoms, then these aluminum atoms donate electrons to the substance, to the substrate. These electrons are transferred to the gold, which then becomes flat. So this calculation was done by my student Nisha Maman several years ago now. And I put this picture of her because if you see the earring she's wearing, this earring is the three-dimensional nanoparticle and this earring is the two-dimensional nanoparticle. So we can try to understand why this happens. So in this picture, what is shown is how the electronic density in the system changes after you put the gold nanoparticle on this doped substrate. And red lobes means area where electrons are gained. Blue means where electrons are lost. And you can see that the gold has gained a lot of electrons from the substrate. So the last thing I want to tell you, just that, so this was a theoretical prediction we did. We did the calculation on the computer. Shortly after our work, a group in Berlin, the group of Freund in Berlin, did an experiment on not exactly the system we did, but a very similar system. They deposited gold nanoparticles on undoped calcium oxide. This is a scanning tunneling micrograph of it. You can see the gold nanoparticles are three-dimensional. But when they instead deposited them on the doped substrate, you can see that now the gold particles are flat. So this example I showed you to show you the power of doing a computational experiment. We could tell them, if you do this, this is going to happen. And then they could do the experiment and confirm that it actually happened. Okay, so I'm done. The message I want to leave you with is that first principle techniques like density functional theory can be used successfully for the computational design of novel materials, and they can provide insight into why materials have the properties that they do. Okay, so that's all I wanted to say. Thank you, and I guess I'm open for questions.
Thank you, madam. Thank you very much. Actually, we were mesmerized, starting from such illustrious grandparents, and your father was a celebrated mathematician. Um, so naturally, everything was there in the gene or in your home that you will grow to be a scientist. And the way actually you have illustrated everything, and I think that's why probably you are the chairperson of the Women in Science in the trust. So beautifully illustrated actually how 1 hour passed we could not know. Now I think we'll have some questions. Maybe we can look in the chat box.
Yeah, I'll just check in the chat box what is there. Okay, so there's one question. could you, okay, so sorry, it's scrolling as I go. So, okay, so many people have said most important discovery of the 20th century. So that's interesting. Someone says, could you share some of the biggest challenges you faced in your journey as a woman in science and how you overcame them? Also, do share some light on your inspiration and role. So, I would say that the biggest. Okay. So the biggest challenge that I faced, I would say, is you know, obviously I come from a very privileged background. So for me, parental permission was not an issue, family support was not an issue, finances were not an issue. What really was difficult was the mental struggle. And the mental struggle, both with things within myself and outside myself, because people are not always very supportive. I mean, my parents might be, but you also have to work in society as a whole and in the scientific community. I think it's people are sometimes very nasty, people say horrible things. And I also think that there is a tendency for people to be especially skeptical of women scientists. They do not believe that women scientists, not everybody, of course, but there are people who feel that women scientists cannot be as good as male scientists. And also, you feel very lonely sometimes as a woman scientist. As I showed you, sometimes you are the only woman in a huge group of men. And unfortunately, our society is such that if, as a woman, you start mixing a lot with the men, sometimes people gossip, they say nasty things about you. So these are some of the challenges. And this, I think, self confidence becomes a real problem. So people look at me and they think I'm extremely confident, I'm extremely outgoing. But actually, I am someone who has always had to struggle with self confidence. Like, even when I was in school and college, okay, I used to come first, I used to win the medals, all that. But before every exam, I was convinced I'm going to fail. And I would cry before the exam, I would cry after the exam. And now, also, sometimes I feel, oh, I'm not a good enough scientist. I will not be able to solve this problem. And for the inspiration and role models, I earlier in my career, I was very inspired reading about the lives of, scientists like Einstein, Feynman, etc. As I grew older, I realized that these people are very inspiring in the science they did, but their lives are not necessarily so inspiring. Many of them were actually very bad to the women in their lives. What I have found extremely helpful is to have support of friends, both male and female friends, but especially female friends, not necessarily in the same institute where I work, but a network of female friends across institutes, across cities, across countries who support each other. This is very helpful. The next question is, how practically DFT is used to know material properties in computational nanoscience. As I have tried to show, but I didn't have enough time to show in detail. By a DFT calculation, you can calculate many properties of a material. You can calculate its structure, you can calculate its, I don't know, like bulk modulus or hardness, you can calculate its magnetic properties, you can calculate its electrical conductivity, its thermal conductivity, etc. So if you have a target, for example, you want to design a material that is a very good magnet, for example, then you can say, okay, let me study all the magnets I know about. Let me understand why they are such good magnets. And let me use this knowledge to try and make a material that is an even better magnet.
Madam, there is a question from Ambassador Dr. Basham. is the ambassador of the Arab Republic of Syria to India for the equality of chances between men and women. Do you think that we need to see a change in culture in some societies or maybe in the professional nature of certain scientific institutions?
Okay, so I think this is, of course, an excellent question. It's a complex question. So why is it that some countries have higher percentage of women in science, some countries have lower percentage of women in science? It certainly has to do with the culture of the country. But also a culture of the scientific institutions and the scientific community, I think. I do not believe there is completely equal opportunity for women and men, not even in the so-called developed countries. I think there are still people who judge men and women differently. Sometimes they may not even be aware that they're doing this. I mean, recently there's been a lot of study about what is called implicit bias, that is bias that people have without even being aware that they have this bias. So people are not thinking, oh, she's a woman, so I will not give her the job. But without being aware of it, they are judging women by a different set of standards than they're judging the men. And of course, families are very important. What do families encourage women to do? What do families, what kind of support do families give? What role do they expect a woman to play while she is working? As you have seen in the statistics I showed, the percentage of women working in science is very different in different parts of the world. And this certainly reflects social attitudes being different in different parts of the world. But it doesn't always mean something good if there's a high percentage of women in science in a country. I mean, that may seem very strange to you that I'm saying that, but some people have shown that in countries where science is valued highly as a profession, the percentage of women is less. And where the percentage of women is high, like for example, Burma is the country, Myanmar is the country where there's the highest percentage of women scientists. 73% of scientists in Burma are women. But in Burma, apparently, science is not considered a good profession. It is not paid highly. So men don't want to go to science. So, Ambassador, I hope, I understand I haven't given you a simple yes-no answer to your question, but these are some of the factors that we have to take into account.
I think, yes, so you have rightly explained, and I think that question has some connection with the next question. Hello, madam, my question is, what are the differences do you observe or feel between scientific environment in India and other countries?
Okay, so I have worked in 4 countries at length. I have spent about 9 years working in the US, 1 year in the UK, 2 years in Germany, and many, many years in India, but I've also visited lots of other countries. Of course, to start with, the big difference was the amount of money available. Okay, so back to India, we had very little money available for science in India compared to what we had in, say, Germany or the US. Now I feel that difference is not so stark. Now, one thing that the first few years I was back in India, which I thought was better in India than it was abroad, was I felt that we were left free to pursue our intellectual interests. There was not pressure from the government that everything should have an immediate application. Okay? Like nobody tried to control what I work on. Now I feel from the government that everything should result in a product, everything should be applied science, etc. But on the whole, I have to say I am happy with the scientific environment in India. However, this is true only in a few places in India. There are only a few places in India which have very good facilities, very good people working there. Unfortunately, in many places in India, the facilities are not so good because the money is just not there. Whereas if you look at US or Germany, there's lots and lots and lots of places which have good facilities. But I have to say, in India, we're still way better than many other developing countries. I have been to many other countries where they really do not have good facilities and nor do they have a strong scientific culture. So in that respect, I think we're doing very well in India.
We'll take the next question. Yes, please ask your question.
Good evening, ma'am.
Hello.
Good evening, ma'am.
Good evening.
My question is how the lowering of dimensionality and reduction of size affect material properties in nano level.
Okay, so this is, of course, an excellent question. And that's what most of my science is looking at. It can affect it in lots of different ways. And I'll just give you a few examples. Okay. For example, something that is not magnetic when it is big can become magnetic when it's nano-sized, or something that is unreactive when it is large can become very reactive when it is small. For example, if you take, I gave you this example of the gold particles, right? So gold, I mean, we use jewelry, we use gold for jewelry, right? Now, why do we like gold so much? Part of the reason is that gold is not reactive. Like if you have a gold chain or gold earrings, it does not become black. Whereas if you have a silver chain or silver earrings, it becomes black. That is because the silver is reactive, it gets oxidized. So gold is inert. That's why we call it a noble metal, because it doesn't react much. But if you take a very small gold nanoparticle, that is not true. It becomes chemically reactive. So these are some of the ways in which properties change. There are lots of other, the way the atoms are arranged can change, the way the magnetism can change, the conductivity can change. So there are many, many ways in which it can change. Does that answer your question?
I think that answers your questions. That is what madam is asking.
Yes, sir.
Okay. Now we'll have another last questions, madam. What are the methodology you follow to examine material properties after reducing its size?
Sorry, what is the question? What are the methodology
you
okay.
follow to examine material properties after reducing its size?
So the methodology I will follow is I will, as a computational scientist, I will do the DFT calculation. First, I will do it for the bulk material, which I basically take as an infinite material. Okay, and I will calculate its properties. Then I will make it smaller and smaller on my computer in the calculation. And then I will do a DFT calculation, a density functional theory calculation. And then depending on which property I want, the first thing I will always do is to check how the atomic arrangement is different, because that is what ultimately determines many things. So the first thing I will determine is how the atoms are arranged. Like you saw, for example, I discussed whether that gold nanoparticle, whether it will have the three-dimensional shape or the flat shape. That is the most important thing. How are the atoms arranged? Then once I have found from density functional theory how the atoms are changed, then I will do more calculations to look at whatever property I'm interested in. The reactivity or the magnetism or the hardness or the conductivity, whatever I'm interested in. That's my answer.
Thank you, madam. I think we are done with the questions. So before closing this session, I have a request, madam. So sometime
Yes.
physically you pay a visit to our university. I am extending an invitation on behalf of the entire university. So kindly come sometime in when you are free, maybe in winter, so that you can talk to a larger audience physically, at least to our women students. And this university has a almost 50-50, rather 51-49 ratio as far as women male ratio is concerned, male female ratio is concerned. So you will love to visit this university. This is a young university, madam, and it has within, I think, 17 years, 17. This university came into existence in 2007, and we are the 15th best university in NIRF ranking. So you will love to see the research ambience and all other things. So I am extending a personal invitation. Kindly accept our invitation, madam, so that you will love to address our, both our female faculties and female students. So I will write
I,
a formal letter to you, madam.
thank you so much. I would be delighted to do so. And I do want to say that I would like, of course, I want to talk to the female faculty and female students, but I think it's important also that I talk to the male students, because male students also have to realize that women can be scientists. Otherwise, they would, you know. So I'd be very happy to do it. Thank you very
Thank
much.
you,
And I'm sorry
thank you,
that there
madam.
was and I'm sorry there was this problem in joining initially. I don't
No,
know
no,
why
no,
I
no,
couldn't
madam.
join.
No issue at all. No issue. But now we also learned that henceforward we will send both the long and short links.
Yeah. Okay. Thank you.
Okay, thank you very, very much.